And let's see, PEO Ships, we have Emily Novak here to talk through your topics.
Good morning, I'm Emily Novak and I'm the SBIR coordinator for PEO Ships. And today we have 4 topics to go over, and what I'll do is give a brief introduction to them. I'll talk about its current state, and then I'll move on to the objective and kind of what a successful company would look like. If any of these topics interest you and you want to talk to me in the one-on-ones about them, I'm happy to go into any of the detail I know. But if you have more technical questions, please contact the topic authors. With that, we'll go into our first topic, which is the fault current limiting distribution cable. This is with the program office PMS 320. They're the electric ships office. And this deals with using high temperature superconducting technology to limit fault currents. Future ship classes are moving towards integrated power systems, which are able to meet higher power demands. And these demands can come from technologies such as railguns, lasers, high power radars. And it's really important that the power systems not only be able to distribute higher power loads, but also have the capability to limit fault currents so that they remain operable if there's a fault event. So one solution to this, or one way to help an integrated power system kind of stay operational, is by using a high temperature superconducting cable. They react very quickly to fault currents and they enable higher power distribution. A lot of the cables right now, though, are designed for land-based use, and they might not have the degree of size, weight, or safety and energy efficiency. I know there's development ongoing for cables in naval applications, but this one is looking for a cable to be developed, a high-temperature superconducting cable that would react quickly to fault conditions and help to protect the power conversion equipment. The cable should be scalable from 20 to 100 meters and also take into account the logistical and safety challenges. I know Jen mentioned a little bit about some of that when she described her high-temperature superconducting technology. So a successful effort under this topic would develop the concept and demonstrate its feasibility. And then if you move on to phase 2, ask you to develop a prototype that would be tested at a reduced scale voltage. The point of contacts for this, the topic author is Jake Kephart, and his number is 215-897-8474, and Mark Uva, and his number is 215-897-8962. The technical manager, or the transition manager, is Robert Mitchell, and the program office point of contact is Joseph Tannenbaum. Our second topic is the versatile robotic mission mover and robotic mission module mover, and this is a topic with PMS 385, and they're the Joint High-Speed Vessel Program Office. And this deals with the loading and offloading of containers on JHSV. So JHSV has a lot of different containers and loads that have to be moved up and down the ramps and in and out of their mission bays, and that's a confined space. A lot of the current cargo transport systems have limiting maneuvering capabilities, and they handle limited load weights, and they also require multiple operators. And then occasionally there's separate tractors and support equipments, which makes it a little bit more difficult to move the containers. The current system on board JHSV can move up to about 18 metric tons, and what this topic is looking for is for a mission module mover that could move a 20-foot ISO container and handle up to a weight of 24 metric tons. So they're looking for the container to be moved from a pier up the stern cargo ramp and into the mission bay, and then also be able to do the reverse. And ideally, the mover would be reconfigurable, so it could move trailers, small boats, and other systems that are on platforms. The requirements of this topic ask that the mission module mover be self-propelled with a rechargeable energy source, and they'd like the mover to be able to move containers in and out of the confined spaces and be able to operate autonomously, or at least with a single operator using a wireless system with a backup hardwire system. This topic talks about kind of the maximum pressure allowed on deck. It says it should not exceed 130 pounds per square inch, and it has to be done within a mission bay that has a maximum overhead ceiling height of 15.5 feet. So successful companies would develop a design concept that identifies an appropriate energy source, and they ask that the energy source be able to do at least 3 transits before having to be recharged. And the company would also conduct a successful business case analysis. If the company moves to phase 2, they'd ask you to develop a detailed design and fabricate a full-scale prototype for test and evaluation. The point of contacts for this task are Stuart Ullman and Dave Lease. And Dave Lease is from the PMS 385 program office, and Stuart Ullman also is kind of associated with that office. But Stuart's number is 301-227-5975, and Dave Lease's number is 202-781-2951. So the third topic is shipboard additive manufacturing 3D printing, and this is with PMS 317, which is the LPD program office. And this deals with using additive manufacturing to help solve supply chain management and manufacture non-critical parts. You guys probably know a lot about this technology, but additive manufacturing uses 3D computer-aided design modeling to create parts. And they do this by layering a material, just layer by layer. And the benefit of this is that it allows a wide range of parts to be created from a single manufacturing system. So that's one of the systems up on the quad. But the Navy is looking to integrate this technology for use on board ships, so ships already at sea, and they're looking for this technology to help them reduce supply chain kind of delays because there's a lot of issues with replacement parts. Currently, you can only get replacement parts through your supply center, or you have to do really expensive helicopter or ship-to-ship transfers. So they're looking to get away from that and be able to solve a need as needed. Additive manufacturing enables non-critical parts to be available on an as-needed basis and also helps to eliminate the delivery costs. Overall, it helps to limit the system downtime. The existing systems that are out there are more for land-based use, and they're designed for printing in controlled environments. And they use materials that don't meet Navy requirements, which is specifically fire, smoke, and toxicity requirements. These systems that are on ships must be able to deal with high humidity and motion. So a successful effort would produce an additive manufacturing methodology for a shipboard environment and produce ready-to-use final component parts that pass Navy fire, smoke, and toxicity requirements. The end goal is a qualified printer and materials that would be installed aboard a ship and utilized. The point of contacts for this are Benjamin Buford, and his number is 301-227-5135, and Jennifer Walk, 301-227-5014. Our fourth and final topic is the Cyber Forensic Toolkit for Machinery Control, and this deals with the cyber defensive shipboard systems. And shipboard machinery control systems are monitored and controlled by a system called SCADA, and SCADA stands for Supervisory Control and Data Acquisition. It's a really important system to protect since they're kind of monitoring everything, and one way to protect it is to use forensics. And forensics would help before and after a security breach, and also help with troubleshooting and identification of non-malicious events that could cause system malfunctions. Forensics would basically just collect and analyze digital data from different sources. So the challenge with forensic analysis of SCADA systems is that the system components are often resource constrained. This depends on the availability of a processor, a memory, and other resources. And a lot of the systems within SCADA are legacy systems, and it's kind of hard to access a lot of the data in them, so they're found at different layers of the architecture. So log data is very challenging to collect. So in general, the log data collected can be inadequate, and the amount of data, or conversely, the amount of data collected can be really large and complex, which makes analysis of it challenging. So this topic seeks a solution that would incorporate data acquisition tools to support forensic analysis of it. and most importantly is one that would have minimal impact on the overall operation of the control system. A successful toolkit should be able to interface with the SCADA system, the Weasel board, which I looked up and it looks like is roughly an analysis system that captures communications, and also ICAS, Integrated Assessment System, for reconstruction and replay of an incident. The forensics toolkit should operate as an open source forensic kit and have open system architecture, and a successful company in phase 1 should be able to define and develop a concept and then use modeling and simulation to demonstrate performance and feasibility. And then under phase 2, you develop a prototype of the forensic toolkit and have testing to be conducted at a land-based facility. So the point of contacts for this are Frank Faris and Rocco Arizi. And Frank's number is 215-897-8716, and Rocco is 215-897-1479. So that's the end of my topics, and I thank you guys very much for listening. And if there's anything you want to talk more about, I'd love to see you in the one-on-ones.